So again, for part C, y equals f of x is that original solution, original equation, when x is 0 and y is 1. It goes through that point. We want to figure out, is there a relative minimum, relative maximum, or neither at x equals 0? And don't forget to justify your answer. A lot of times you guys don't justify your answer and lose that point on the AP worksheets. So to figure this out, normally, to find a relative min, relative max, what we would do is take a look at the derivative, figure out when it's 0 or does not exist, and then do a number line. Right? Figure out is it changing from positive derivative to negative, then it's a relative maximum. If it's changing from negative to positive, it's a relative minimum. Again, this is a little bit different because we've got that x and y in there, so it doesn't work like that. So we have to use a different technique, and we learned this a while back, but we didn't use it as much as we did the number line. So we're going to kind of review it real quick. And it is the second derivative test. With the second derivative test, we don't have to do a number line. If we know a couple things, we can figure out if we have a minimum or a maximum. First thing is, if the first derivative of f equals 0, right, that tells us we're going to have a critical point, and it could be one of those two things. It could be a relative minimum or a relative maximum. So for our three different scenarios, that has to be true. Derivative is going to be 0. For the first one, if the derivative is 0 and the second derivative is greater than 0, so we're going to have a horizontal tangent line. Right, that's what the first derivative is telling us, is being 0. And second derivative is greater than 0. What does that tell us about the graph? Concave up, right? Second derivative is positive, it's concave up. What kind of point do we have right there? We have a local minimum, right? Derivative is 0, second derivative is positive, we have to have a local minimum. If the first derivative is 0 and the second derivative is less than 0, first derivative is 0, horizontal tangent line, second derivative is less than 0, that means it's going to be concave down. So we have a local max. Well, if first derivative is 0 and second derivative is also 0, it's going to be neither of these. Most likely that's going to be an inflection point and not a local min or a local max. All right, so if we know the first derivative and the second derivative at a specific point, if that first derivative is 0, we can determine if it's a local min or a local max. If the first derivative is not 0, it's not going to be a local min or local max. It could be if the first derivative was did not exist, but we wouldn't be able to use the second derivative test because if the first derivative doesn't exist, we're not going to find the second derivative at that point either. All right, so let's take a look. We need to figure out two things. First, we need to figure out what's the derivative at 0, 1. So remember, our derivative, dy dx, is 1/2 x plus y minus 1. So we're doing this, our point is at 0, 1. So if we put 0 in for x, 1 in for y, we get 0 plus 1 minus 1, which is 0. So our first derivative is 0. So we know it's a critical value. It could be one of these points. The next thing we need to do is figure out that second derivative. And that was 1/2 x plus y minus 1/2. So we're going to put that 0, 1, that point in here. So we get 0 plus 1 minus 1/2. We get a positive 1/2. So our derivative is 0. Second derivative is greater than 0. That means we have a local minimum. And this is what it's talking about with the justification. You need to kind of explain why. You have to check the second derivative and the first derivative. And it doesn't hurt to write it out in your explanation. At x equals 0, the first derivative is 0, and the second derivative is greater than 0. Therefore, there is a relative or local minimum at x equals 0.